see. Okay, that's good. So as I say, this chi-square test is for studying correlation between two categorical variables. In fact, this, I should say, it's contingency table analysis. So I use contingency table. It can help you to display the joint frequency distribution for a pair of qualitative variable and to understand what's going on, whether there's correlation between them. Of course, sometimes you can split the contingency table, right, using additional variables to maybe include possible confounders in the analysis, right? So, but we're going to look at just the most simple one, okay? I'm going to use this example to review. I think you probably have all gone through this. That's actually 2 weeks ago, right? In Pagano's book, when it talks about analyzing proportion, category data, studying proportion, okay, you learn tests of one proportion, and there's also tests for difference between two proportions, right? Let's say you have two populations, and you want to check the percentage of people who have maybe a certain type of disease or not, right? So you can use having disease or not as one variable, and population, one, population two is another variable, and then use a chi-square test to do it, right? You don't really need to use a test of difference between proportion, because this chi-square test also can be used for that purpose. So in fact, it's better to use chi-square test because you can add another categories of population, so you can study 3 population, 4 population at the same time, right? So it's actually a more powerful tool. So actually in the lecture I didn't even mention that, right? That testing difference between two proportions, because chi-square test is good, right? So this is an example actually for studying correlation between two categorical variables. Right, this kind of study has been done in the 80s a lot. Right, people try to understand whether there's aspirin can help us to prevent heart disease or not. It's a blood thinner, right? So I think nowadays most people know that. So the study involved 300 people, and then 150 of them used placebo, 150 of them used aspirin. And after a period of time, when we observed these people, that 50 of them had heart disease and 250 of them had no heart disease. Okay, but if you observe each group, treatment group, placebo group, right, 36 out of 150 had heart disease, and aspirin 14 out of 150. Okay, seems like placebo have higher rate of having heart disease. Right? But does it just happen by coincidence, right? Or there's really something going on there? So what we can do is, as statistical, we can use this chi-square test, right, to help us to check whether the two variables really are correlated with each other or not, right? If they're not correlated with each other, that means there's no really treatment difference. Then we expect a percentage distribution, outcome distribution, I should say, for placebo group, and then aspirin group should be about the same. Okay, and so we use this chi-square test for it, and what's the null and alternative? Anytime you're doing hypothesis testing, you procedure-wise, you got to have a null and alternative hypothesis set up. Okay, so for a situation like this, null hypothesis, since we're studying correlation, right? So the null hypothesis that there's no correlation, okay, or no difference in the outcome distribution. For placebo group and aspirin group, the outcome distribution are the same. That means percentage of AS and no, they're the same between these two groups. Okay, and the alternative, of course, is opposite to the null, right? There is correlation. So it's pretty easy to state. Now, when I read your graduate assignment paper, I realize a lot of you have trouble stating the hypothesis, right? And especially try to use those notation. If you're not comfortable with those notation, you don't have to use those mu, whatever equal, those notation. You don't need to. You just write a phrase, right? A sentence or a phrase to describe the null. Null for testing mean, null is what? Mean equal to certain value, alternative is mean greater than or less than. Just write it out instead of using math notation. It's fine, right? So like in this case, you can write the null hypothesis be there's no relation between treatment variable and outcome variable. And alternative that there is a relation or correlation between treatment and outcome variable. Okay. So if you look at this slide here, right, this is original data, okay, And in this slide, actually, I add some information here. Things in the parentheses, these are called expected frequency, right? 36, 114, 14, 136, these are what we actually observed. And then if the null hypothesis is true, if null hypothesis is true means that proportion distribution or outcome distribution for placebo and aspirin should be about the same. If you look at the overall proportion, it's 50 and 250. So for yes and no, having heart disease or not, it's 1 to 5. Okay. So if there's no correlation, we expect that the outcome distribution for placebo group is also 1 to 5, right? And for aspirin group also 1 to 5. So among those 150, we can split it into 1 to 5 counts, right? 1 to 5 is like 25 to 125. That's 1 to 5 ratio. Same thing for this group. In total is 150, right? 1 to 5. Okay. If you have, instead of having 150, let's say you have 60, then that'll be 10 to 50. Okay. Hope that makes sense, right? This is a situation that both treatment groups are the same size. This is so-called a kind of balanced design, right? But there might be a situation that you don't have 150, you have 100. If you have 100, then this would, I'm sorry, 60, then this would be 10 to 50. So that's still 1 to 5 ratio. Hope that makes sense, right? So these, we call them expected cell counts when null hypothesis is true, when there's no correlation. And the 36, 1400, 1436, these are observed cell counts. And the chi-squared test statistic for testing correlation is based on the difference between the observed and the expected frequency. Okay. If the difference of the observed and expected frequency is high, then we believe that there's strong correlation, right? Okay. Does it make sense? Right? Okay. So actually, so you understand how to figure out these expected cell count. Once you found the total from each column, then if you know the row total, split that row total into the same proportion, you'll get that, right? But there's a formula you can follow. That is, if you wish to figure out this expected cell count for this cell is on the first row and first column. You just use the first row total times first column total divided by grand total. That will give you this number. Okay. This will be this row total times this column total divided by grand total. So let's say if you have 60 here and you have 50 here, okay, then 60 times 50 divided by whatever total here, you will get that number. Okay, so that's a formula. Actually, the next slide talk about that, right? If you want to figure out the expected cell count, right? MI stands for I's row total, and J stands for J's column total, T is grand total. So if you want to figure out expected cell count from the I's row and J's column, just use the I's row total times J's column total divided by grand total. You get the expected cell count, right? Now our situation is actually simple. It's a 2-by-2 table, right? So it's pretty easy to calculate, right? And plus, actually, we have same row total, so actually outcome for both rows are the same, right? Same pattern. And then how do we figure out the difference between the observed and expected frequency? What we do is actually use a difference for each cell, find a difference between observed and expected, like this 36 minus 25. And we square it. Okay, squaring it so that it won't have cancellation, right? So we square it to actually get the absolute difference or actual positive difference. Square that but divide by expected cell count. You do that for each of those cells. We have 4 cells, so we do that for all 4 cells and add them together. That's how we form this chi-square statistic. So it helps us to measure the difference between the observed and expected frequency, right? Expected frequency is the expected frequency under null hypothesis, right? So we use the observed evidence and to see how far it is from the null hypothesis. If it is far, then the chi-square score should be high. You're going to accumulate more differences, right? So this chi-square test is like kind of one-sided test. The larger the chi-square score is, the more likely you're going to reject the null hypothesis. Okay. So it's a chi-square test, but chi-square test is actually a skew and positive distribution. It only takes on positive number. And this distribution has a degrees of freedom. It has one parameter, degrees of freedom. And what is degrees of freedom? Degrees of freedom is number of row category. For that row variable, like a treatment, all right, we have 2 of them, so R is 2. Number of column category, number of categories for column variable. Like our column variable, we have 2, right? 2 minus 1. So for this particular case, it would be 2 minus 1 times 2 minus 1, so that's 1. Degrees of freedom for a 2 by 2 situation is 1. So this chi-squared statistic has a degrees of freedom 1, right? So this tells you that we could have 2 by 3, 4 by 5, all kinds of possibility that can happen, depends on the variable, the type of variable we have. And such a test is actually a large sample test. When sample sizes get large, such a statistic asymptotically follow a chi-square distribution, right? So when you run the software, in some places they may use the term asymptotic, right? That means it's a large sample. And what is proper condition, right, for a large sample? The Cochrane's guideline kind of give us a suggestion what can be considered as a large sample. And that is none of the expected cell count are less than 1, right? So when we do this study, all the expected cell count are greater than 1, so that's good, okay? And then no more than 25% of the expected cell frequency that is less than 5. What does that mean? We have also totally 4 cells. If one cell, right, the expected frequency is less than 5, that consider 1/4 of the cells, right, 25% of the cells. So for a 2 by 2 situation, if you observe one cell, its expected cell count less than 5, that already violated the large sample condition, right? We want all of them has expected cell count greater than 5. So that's what the Cochrane's guideline is about large sample, okay? So if that condition is satisfied, then we can use a chi-square distribution to evaluate the significance of this evidence, right? And what we do is actually from that chi-square distribution, once you found this score here, you figure the area to the right of it, right? And that's a p-value. This area to the right of it, this would be the p-value for the test. Okay, of course, if you have R, command it'll just produce that for you, okay? So that's really good. For this particular case, actually, we have 11.616, and then if you look up a chi-square distribution table, this is a chi-square table from Pagano's book. Degrees of freedom 1, if you have a chi-square score 3.84, the tail area is 0.05, okay? And R is actually 11, so 11 actually out of the range. 11 somewhere here. So if you have 10.83 p-value is 0.001. If you have 11 p-value even smaller than 0.001, right? So if you try to use the table, right, you see the significance of it. You know the p-value is definitely less than 0.001. Okay. Of course, with the software, right, that's even better to give you the exact p-value. In this case, the p-value is less than 0.05, so our evidence is statistically significant at 5% level. Okay. So that's it, right? It's very simple, right? Okay, so that's one example using studying aspirin, how the use of aspirin, how aspirin may be related to taking aspirin may be helpful for reducing chance of heart disease. And often, if you find significant, then people will calculate these either relative risk of odds ratio, depends on what kind of study you're involving in, right? If this is cohort study, a prospective study, usually people will look at the relative risk, which is ratio probability of having disease in this case, right? So the chance of placebo group to have disease is 36 out of 150. The chance of aspirin group, right, to have disease is 14 out of 150. Ratio of that is 2.57. This number is a relative risk, right? You use a ratio of probability of getting disease, right? So this tells us that if you took placebo and didn't take aspirin, your risk of having heart disease is more than 2 times, right? 2.57 times, right? Than those who did take aspirin. So this is a relative risk statistic. Okay. Hope this makes sense, right? Then this is just another situation. We have not 2 by 2, but 2 by 3. This is a study that we try to evaluate different type of treatment to help people get rid of drug habit. Okay. So first treatment, each treatment we have 24 subjects involved, and first treatment used discipline 14 have no relapse, right? And the next two placebo and another treatment, actually 6 and 4 no relapse. So it seems like the discipline is doing a better job, but we don't know whether this is just by chance, right? So we want to understand the significance of this, so we run a chi-square test for independence between 2 variable, treatment variable and outcome variable, right? Now, this chi-square test for independence, there's another name for it. People also call it chi-square test for homogeneity. Homogeneity of what? Of distribution. The outcome distribution, are they the same? Okay, so again, like I said, this test can be used to compare difference between proportion between populations, and it can be extended to 3 groups or 3 population, 4 population or more, right? So it's really great. If you calculate total for no relapse and have relapse, 24, 48, right? So it's a 1 to 2 ratio. So if each group, treatment group have 24, the expected outcome under null hypothesis would be 1 to 2 ratio will be 8:16. So I have 8 to 16, right? So in case I have one row treatment group is like a 12, if you want to have 1 to 2 ratio, it'll be 4 to 8, okay? So that's if you don't remember that formula, but you understand the idea, right? That, the equal distribution. So you can use the ratio of the total to figure out how to split this number to get into the expected cell count. Okay. And of course, null hypothesis for this study is there's no treatment difference, right? The outcome distribution are the same. Or we say there's no correlation between treatment and outcome. An alternative, of course, there's a correlation between treatment and outcome. And what we do, again, we just measure the difference of each pair, right? Observed and expected within each joint, each cell, squared, divide by expected cell count. Do that for all 6 cells. Okay, so you add them all to all 6 cells. You get that chi-square statistic. Again, the larger the score, the more likely that you're going to reject the null hypothesis, the more extreme the evidence is. Right? And this problem, we have 3 rows and 2 columns. Okay, so 3 minus 1 times 2 minus 1, you get 2. So that's the degrees of freedom. You will use that to check the chi-square distribution table to figure out the p-value. Our score is 10.5. Now, if you look at the chi-square table, this is part of the chi-square table. Degrees of freedom 2. If you have a chi-square score 9.21, the tail area is 0.01. If it's 13.82, tail area is 0.001. Our score is 10.5, right in between them. So our p-value is between these 2 numbers. If you use a table, right? If you use the software, then once you specify the degrees of freedom, you know. You can use Excel to figure that out. Right? But if you have a data, you have the R commander, then R commander to just do everything for you. Okay. Hope that makes sense. This is a simple test. I think for the year that I've been teaching statistics, most of the students think this is the easiest test to learn, right? Then t-test or whatever test. Right? The concept is easy to grasp. Okay, so I think that's good. And here is another version of it. It's called Yates correction test. Right? What it does is actually correct that difference of observing expected by 0.5. Right? This correction for continuity. If you remember, you probably studied the normal approximation to binomial, right? In one of the sections. Sometime calculating approximate discrete distribution using continuous distribution. People believe that may not be as good, right? So they try to do a little adjustment to it, right? And that's the reason, right? So usually the outcome is about the same. Okay, so you don't really have to worry about it. But most of the time, if you run the software will have the option if you want to take a look at that, right? I think the outcome will be about the same. If you run the chi-square test. You click statistic, contingency table, and I don't have data, right? So I can actually, but I have organized data, right, in that contingency table. So I can click contingency table, enter, and analyze two-way table. I click on that, and I can just put in those frequency in here, right? If you need the 2 by 3 column, just scroll this down, you get this, right? Okay, so you can enter, you can change number of column, number of rows, right? So in our data, we have 36, 114, and 14, and 136. That's easy, right? If you want to report the percentage distribution row-wise or percentage distribution column-wise or overall percentage, right? You can check these buttons, right? So you're probably interested in row percentage. And then we have a chi-square test or independent check. That means it's going to run a chi-square test, right? Or there's at the bottom here, it has actually so-called a Fisher's exact test, right? I can have that check too. What is Fisher exact test for? Now, our data actually is categorical, right? So the actual distribution for the statistics is supposed to be discrete, right? Chi-square is actually approximation. Chi-square is a continuous distribution. We use that to approximate the sampling distribution of the test. In fact, this test statistic has its exact distribution. So Fisher recommends that people use that, right? But when we have large data, actually Fisher's exact distribution is hard to compute. So that's why we have a chi-square option, right, to deal with large sample. So if you have sample size that is small, you check the Cochrane's guideline, and then it doesn't satisfy the large sample condition, then you're better off with the Fisher's exact test. Okay. And also, if you like to check the expected frequency, you can ask for printing expected frequency, just to help you to check the large sample condition. Right. So if I have these checked, I click OK, and SPS will give me outcome. We have a p-value right there. Right. That's a very small p-value, 0.00099. Right. That's very small. Okay. And it also gives us an odds ratio statistic. Okay. And odds ratio, this is actually the confidence interval. Right. So I should have something. Yeah, expected outcome. Oh, actually, this is Fisher exact, right? And then Pearson's chi-square test has a p-value of 0.00066. And you have the contingency table. Expected cell count also shown there, right? 25, 125, that's what we get there. Okay. Okay, so it's very simple, okay? All you need to do is fill in the information in that contingency table, and you can run the analysis.